before we start again, so shout out to our partners, Hello Gold and ETHKL, for taking the time from their day jobs to bring people from around the world over. And especially thanks for our speakers from Akomba Labs, Ethereum Foundation, and all the way from Switzerland, Chain Security. Before we start to get our guest speakers to speak, one of the things that we do at ETHKL is we get one of our local developers to just give a small demo or presentation on stuff that they've been working on. So can we get Ken Chan? Let's introduce Ken for a bit. So Ken's a blockchain developer. He was working with Omnilytics. One key interesting trivia I didn't know, Ken apparently created the most popular chat app for Pokemon Go in Hong Kong. Just a random stuff that we find out. But please feel free, give a round of applause for Ken.
Hello.
Right. Welcome everyone. Since it's your first time here, I will try to make a good impression of ETHKL for you guys. Right, so I'm going to introduce to you what are zero-knowledge proofs. So zero-knowledge proofs have been popularized recently by another cryptocurrency, ZK, and I'm going to run you through how it actually works. Right, so let's run through a very classical example of an election on Ethereum. Let's see if it's possible, right? So how we will do it is first we will have a smart contract and Trump and Clinton, right? So they'll be started with 0-0 and they'll be competing against each other. So how it will be classically done in Ethereum is that we will have voter 1 will be voting for Trump +1, voter 2, and so on. So after that, we can conclude that Trump, since Trump has the most votes, is the winner of the election. But obviously, this is a very suboptimal way of doing things. Why? Because we can see that the voter 1 and voter 2 is actually exposed. So they can actually be politically targeted, or miners can actually prevent those votes from actually entering the system since they control everything that enters into the blockchain. Right, so the most optimal way of doing this is actually to hide who they vote for. So each voter will actually cast 2 votes, one for Trump and one for Clinton. So how it's going to look like is that voter 1 will actually +1 for Trump, and voter 1 will also +0 for Clinton. So that indicates that the voter 1 wants to vote for Trump. So this is the optimal way of doing things, and at the end of the round, we want to conclude that Trump wins without actually displaying the total number of votes. So let's run through how we can do that with zero-knowledge proofs. Right, so zero-knowledge proof, the definition, the high-level definition of it is a prover can prove to a verifier, which is another party, that they have knowledge of X without revealing information about X. Okay, this seems a bit paradoxical, right? So let's say I know Hari's birthday, and he asked me to prove it to him that I know his birthday. How will I do that? I'll just say his birthday out, right? So that's the only way to prove it. But in cryptography, you can actually you can reveal that you know something without revealing that something. Let's see how we can run through that. Okay, so first I'll give you an example of a zero-knowledge proof. So I will need a volunteer. Harry, can you help me out? Right, okay, so stand here. Okay, so I have 2 pens, right? Can you hold it? Like that. Yeah, okay, so I have 2 pens here. So one is a blue pen, one is a black pen. So assume Harif is colorblind, right? Assume Harif is colorblind. And colorblind means you cannot differentiate between blue and black. So your eyes are open when you're colorblind. You're not blind. Open your eyes, right? Okay, so assume Harif is colorblind, and he asked me to prove to him that these 2 are different colors. Because he's colorblind, he cannot know such a thing. So I want to prove to him that these 2 are different colors without revealing the actual colors, that this is a blue pen, this is a black pen. how will I do that? Okay, so first, Harif will actually put the 2 pens behind his back, and then you can choose to either shuffle or not shuffle the pen. So, okay, try not shuffling. Not shuffling means you're not doing anything. Okay, take it out.
Okay.
Yes, okay, face there. Right, so here we can see that the order has not changed, blue and then black, right? So we can see, so I can say to him, okay, the pen has not been shuffled. Then Harif will say, okay, yeah, you're right, I haven't shuffled it because I know I'm the one shuffling it, right? Okay, so there might still be the chance that I am guessing. There's a 50% chance that I'm right. So let's try that again. This time try shuffling. Okay, take it out. Right, so I can tell him that it's not shuffled because the order hasn't changed. Blue and then black, right? So we can play this game on, and this decreases the chance that I'm right. So what does this mean? So this means that I can actually prove to Harif that I know the 2 different colors are different without actually revealing the colors to him. So that's quite mind-boggling to me initially, right? So as it turns out, the 20th round that you're doing this, you can actually decrease the chance to 1 in a million. So ZK SNARKs are one of the other things for zero knowledge that a lot of cryptographers are using right now. So it's almost like a branch of it. There are a few techniques that are used. This is one of them. So I won't cover about all the other definitions, but what it stands for is zero knowledge. Zero knowledge is the example that I've given you just now, that you don't reveal knowledge about something. So what I'm going to cover is succinct and non-interactive. And arguments of knowledge just means that it's an assertion of truth. Right, so what does succinct and non-interactive mean in ZK SNARKs? It's one of the technique used. So succinct means that a prover, which means that it was me just now in my example, generates something called a proof string. So proof string is like a small text file kind of thing. It runs a few kilobytes large. It means that it is succinct because it is a small proof string. And then you have a verifier who actually verifies that the proof string is correct. So this is the meaning of non-interactive. This is only a one-step process where the difference is that the example just now, it was an interactive example where we actually verified against each other 20 times. So this happens only 1 time. That's why it's more efficient, right? Okay, so how it works is that, I'll just cover this very briefly. So how can we make a smart contract private with ZK SNARKs, right? So how it works on a very broad level is that we turn a code into a bunch of circuits. So this bunch of circuits are basically like gates where, let's say a plus represents a gate, a multiply represents a gate. Then on the other hand, it'll generate out something called toxic waste. So this toxic waste is almost like a dangerous parameter that can be used by an attacker to actually attack the network by creating something we call false proofs, which I'll cover later. Right, okay, so generating a proof, okay, verifying a proof. So verifying a proof, the output would be either true or false, whether the proof is correct or not. So maybe after this presentation, I can go into the discussion if you guys are interested. Okay, so using the toxic waste, you can actually generate some fake proofs. So in the case of, let's say, Zcash, you can actually print more money. You can create more supply of Zcash coins. Right, so why are ZK SNARKs popular nowadays? So I'm going to cover that. So it has certain properties that make it very strong cryptography, and it's led by the Zcash team. So its math is backed by math. The difference with other private cryptocurrencies like Monero or like Zcoin is that it's not coin joining, it's more of very solid cryptography. So the other point about ZK SNARKs that are very important is short proofs, because like we see just now that the property of ZK SNARKs is that it's succinct, means that it's verified very quickly. So the disadvantages of ZK SNARKs is that, like we can see, there is a trusted setup for every program or every contract that you want to execute. So this actually brings in the issue that you need to actually find a way to dispose of the toxic waste, because if you don't dispose of the toxic waste, you run the risk of almost defeating the purpose of your program. Right, so, okay, blah, blah, blah. Okay, computationally expensive. So this you can actually observe in cryptocurrencies like Zcash, where it takes a few seconds to actually verify a transaction and generate a proof. So this is why ZK SNARKs are still not as popular. So in Ethereum, right, so there are a few tools out there, but they are not as popular. We have Socrates, which is the ZK SNARK toolbox. What it does is that you send in a smart contract and it generates out some the circuits, the ZK SNARK circuits, like I mentioned before. And then, yep, all the other libraries. Okay, thank you.